In today's lesson, we're going to look at the process of separating the variables to solve differential equations involving functions in both x and y. But to start off, we'll have a recap and look at what we did in our last lesson. So we're going to start off by finding the general solution of the following differential equations. So let's look at the first one. We have dy by dx minus y equal to 3. Right, you can pause the presentation if you like and have a go at doing it yourself and then check your answer at the end. Right, to do this we're going to first of all start off by rearranging the equation, which will give us dy by dx equal to 3 plus y. And because we then change this over, invert it if you like, to give us dx by dy equal to 1 over 3 plus y. And we can now rearrange to give us dx equal to 1 over 3 plus y dy. And so integrating both sides will give us this. And we can now integrate, giving us a function in x, where x is a subject, and ln 3 plus y plus some constant c. Now I'm going to rearrange this and say, okay, well x minus my constant c, if you like, is equal to ln 3 plus y. But I don't like this negative constant here, and we can rewrite this as, we can say, okay, well let minus c equal some other constant, let's say c dash. So this makes the right hand side equal to x plus some c dash is equal to ln 3 plus y. So we want y, we want to work out what y is equal to. So now we can say that e to the x plus our constant is equal to 3 plus y. Now, looking at the left hand side here, using our laws for indices, we can say, but e to the x plus our constant, just a minute, let me just rub that a little bit out, a little bit of mistake there, e to the x plus our constant c can be written as e to the x times e to the some constant c dash. And now I'm going to say, well, I'm going to say, taking let e to some c dash equal a. So now, rearranging our equation here, I can say y is therefore equal to a e to the x minus 3. And there we go. We've now rearranged and we've found a general solution for our differential equation. Moving on to our second example, we are asked to find the general solution for x squared minus 1 dy by dx equal to x. Rearranging this will give me dy by dx equal to x over x squared minus 1. And again, rearranging, I can say dy equals x over x squared minus 1, and then integrate both sides. Integrating both sides, I can see on the right hand side that the derivative of x squared in our denominator is 2x. So if we just play around with the right hand side, I can say that a half times the integral of 2x over x squared minus 1 with respect to x. And integrating this will give me y equals a half ln x squared minus 1 plus some constant c. So today we're going to understand the process of separating the variables to solve differential functions of both x and y. So far we have solved differential equations involving dy by dx and either a function of x or a function of y. We also need to be able to solve differential equations which involve both functions of x and y. For example, we have xy squared dy by dx equal to x squared plus 1. So to do this, we have to first of all separate the variables. We need to rearrange to get just y on one side and x on the other, and then integrate both sides. So we'll have a look at this example here. We're going to find the general solution of xy squared dy by dx equal to x squared plus 1. And so you can see here we've got functions in both x and y. So taking this, we can say, rearranging, we can say that y squared dy by dx is equal to x squared plus 1 over x. And taking the right hand side, I can simplify this by writing both these functions as writing it as two separate fractions and cancelling down to give us x squared over x will become just x plus 1 over x. And I can now rearrange this again to give us, I rub that out now, respect to dx, and then integrate both sides. Right, so integrating y squared with respect to y will give us y cubed over 3, and integrating the right hand side we can say the integral of x will give us x squared over 2, and the integral of 1 over x is ln x plus our constant c. Right, so I'm now going to multiply through by 3 to give us y cubed equal to 3x squared over 2 plus 3 ln x plus 3 times our constant c. But I'm now going to say, just to make it look neater, I'm going to say, okay, let k equal 3c. So our final solution will be y cubed is equal to 3x squared over 2 plus 3 ln x plus k. We're now going to look at another example. We want to find the general solution of dy by dx equal to y over x squared minus 1. And we've been asked to write our answer as y equals some function of x. Right, so first of all, we're going to rearrange our equation. So I can say that 1 over y dy is equal to 1 over x squared minus 1 dx. And the denominator here, we've got the difference of two squares. So 1 over y dy is equal to 1 over x minus 1, x plus 1 dx. So now we've got this in some form that we can integrate. So taking this, I'm going to integrate both sides. That's us. And looking at the right hand side, we can see now to integrate this, we need to separate it and write it, separate it into two partial fractions which we can then go on and integrate. So taking the right hand side, I'm going to say okay, the 1 over x minus 1, x plus 1 is equal to a over x minus 1 plus b over x plus 1. Therefore, 1 is equal to a x plus 1 plus b x minus 1. And when I equate the coefficients, I get a is equal to a half and b equal to minus a half. So now I can say that the integral of 1 over y dy is equal to the integral of 1 over x minus 1 plus sorry, that should be a minus because we're going to have minus b minus 1 over 2 x plus 1. Dear, let me try that again. There we go. X plus 1 with respect to x. Right, so now I can see here that we have got, I can take out a half and then integrate both our functions. Right, so going on to the next page, I can say that the integral of 1 over y with respect to y is equal to half times the integral of 1 over x minus 1 minus 1 over x plus 1 with respect to x. So now I can start integrating. So here I have ln y is equal to a half times ln x minus 1 minus ln x plus 1 plus some constant c. Now, using my laws for logs, I can say that ln y is equal to a half ln x minus 1 over x plus 1 plus c. Now I'd like everything to be written in log form, so I'm going to say let c equal ln a. So now I have ln y equal a half ln x minus 1 over x plus 1 plus ln a, which I can now write using my laws for logs again. Ln y equals, I'm going to bring my half up, which becomes x minus 1 over x plus 1 to the power half, which is the square root of x minus 1 over x plus 1, and using my laws for logs, plus ln a becomes multiplied by a. So now I have my final function in y, so therefore I can say that y equals a times the square root of x minus 1 over x plus 1. And there we go. We're now going to move on and look at our next problem. We're going to look at solving the differential equation dy by dx equals x y e to the 2x, given that y equals 1 when x equals 0. Right, so rearranging this, again we can say that the integral of dy over y, do that again, rearranging, we can bring the y over, so we can say the integral of 1 over y dy is equal to, and we're left with the x and the e to the 2x, the integral of x e to the 2x with respect to x. So looking at the right hand side, we can see here that to integrate this function here we need to look at integrating by parts. So we'll say okay, we'll let u equal x and dv by dx equal e to the 2x. Therefore du by dx is 1 and v is a half e to the 2x. Right, so taking the left hand side, integrating this, I can therefore say, using our formula for integration by parts, that uv, which will become a half x e to the 2x minus the integral of v, half e to the 2x multiplied by du by dx with respect to x, which will give me a half x e to the 2x. Integrating this will give us a quarter e to the 2x plus our constant c. Right, so I've now integrated the right hand side. So therefore, integrating 1 over y will give me ln y. I can now say on the left hand side ln y is equal to half x e to the 2x minus a quarter e to the 2x plus c. And writing it in a slightly neater way, I can therefore say that a quarter e to the 2x, so taking out a factor of a quarter and e to the 2x, will give me 2x minus 1 plus my constant c. Right, so what I can now say is when y equals 1, so when y equals 1, x equals 0, so therefore ln 1 is a quarter e to the 0 2 times 0 minus 1 plus c. And rearranging this therefore will make 0 equal minus a quarter plus c. Therefore c equals a quarter. So now I have my final solution. I can now say that ln y is equal to a quarter e to the 2x, 2x minus 1 plus a quarter. Right, now that example is actually taken from the miscellaneous exercise 8's question 5, and you'll find some similar questions to that in the miscellaneous exercise which you'll be doing, which you should do for practice for your exams. I'm now going to look at our final example before you do some work. We're going to find the particular solution of dy by dx equal to minus 3y over 2x when x equals 2 and y equals 4. And again, we want to write our answer in the form y equals some function in x. So taking our question, I'm going to rearrange it. So what I will have is 1 over 3y dy equal to minus 1 over 2x dx. And we shall integrate both sides. So bringing out my third, I can now write the left hand side as 1/3 times the integral of 1 over y with respect to y is equal to minus a half integral 1 over x with respect to x. And integrating will give me 1/3 ln y equal to minus 1/2 ln x plus a constant c. I'm now going to multiply both sides by 3, which will give me ln y equal to minus 3 over 2 ln x plus 3 times our constant c. And it's at this point I'm going to say, take our constant and say, let ln a equal 3c. So now I can write ln y equals ln x to the minus 3 over 2 using our log rules plus ln a. And using our log rules again, I can say that ln y equals ln a times x to our minus 3 over 2. Right, so we're now told that we need to find a particular solution. Let me get my colours right. And we want to find y when x equals 2 and y equals 4. So I can work out what my a is. So when x equals 2, y equals 4, which we're given, which means that I can say that 4, or ln 4, equals ln a 2 to the minus 3 over 2. So therefore 4 equals a the 2 to the minus 3 over 2. Four equals a over 2 to 3 over 2. So 4 times 2 to the 3 over 2 equals a. Now 4 we can write as 2 squared times 2 to the 3 over 2 equals a, which using our power rules means that a, our rules for indices, a is equal to 2 to the 7 over 2. So I'm writing it as a power of 2. Now going back, I can therefore say, now I know what a is, can't write it, just a minute, I can say that y equals a which is 2 to the 7 over 2 multiplied by x to the minus 3 over 2. And just showing, I like to show all my where I get my answers from. So 2 to the 7 over 2 I can write as 2 to the 6 over 2, which is 8, multiplied by 2 to the half, which is root 2 times x to the minus 3 over 2. Which means that my final answer is 2 to the 6 over 2 is 2 cubed, which is 8, times 2 to the half, which is root 2, x to the minus 3 over 2. So my final answer for this, I can therefore write as y equals 8 root 2 x to the minus 3 over 2. I do hope that has helped you, and working through the examples has helped. I've now got a sheet of forming and solving differential equation questions which I'd like you to work through and complete over the holidays for our next lesson.